Section 3.1, Derivatives of Polynomial and Exponential Functions. All right, so through Chapter 2, what we've done up to this point, we started off with the discussion about a limit and what a limit was, what it was that you were describing when you evaluated a limit, and then we started off using, we talked about slopes of tangent lines, right? Which eventually became our derivative. But we started off with tables of values and having to crunch numbers there. Then we moved to the limit laws, direct substitution, maybe rewriting of functions, processes that we could use to evaluate the limit. Then we got into, toward the end of that chapter, the limit definition of the derivative. And so we got back to that idea of what the derivative was. We formally defined the derivative as the slope of the tangent to the curve at a given point, which ultimately we kind of describe as quote unquote the slope of the curve. But what I want you to keep in mind always when you're talking about the derivative, what are you describing? You are describing the rate of change of that function. How are the function values changing with respect to the inputs into the function? So that notation, we had all those different notations for the derivative. We use the f prime of x or y prime. We also use that dy dx notation. I mentioned that one, and that's one we're going to use a lot in this section or in these sections going forward in this chapter as we start to develop the processes that we use to find specific or derivatives of specific types of functions. All right, so that's a note. I always say half the battle is the notation, so you've got to be clear on the notation and what we're using or what we're describing with the different notations that we're using. So again, 2.7, 2.8, we talked about the limit definition of the derivative, but again, that's still kind of cumbersome, right? If I had to use a limit definition every time I wanted to find the derivative of a function, I'm wasting a lot of time doing that. So we need a better way, and of course there is one ultimately. All of these different processes that we're going to talk about over the course of Chapter 3. So that's what Chapter 3 is all about. Now, in finding a derivative, I want you to keep two things in mind. If I'm presented with a function whose derivative I am trying to determine, there are two things in play. First of all, different types of functions require different methods or processes for finding their derivatives. We'll talk about power functions, we'll talk about trig functions, we'll talk about exponential functions and log functions and so forth. So each type of function has its own process for finding its derivative. Then the second thing is there are also broader processes that are used when you have a combination of functions, like a product rule and a quotient rule and a chain rule, these types of things. Chain rule is a big one. We're going to spend quite a bit of time with that one. I'll give you a lot of examples with chain rule when we get there. All right, so there's always these two questions that you want to ask yourself when you're differentiating a function. What type of function or types of functions do I see? And is there some broader process that I have to apply, given the fact that I have a combination of functions, okay? Because what I find to be the case is, as we look at each individual type of function, they tend to go pretty well. If I know what type of function I'm working with and I know the process, it's a pretty straightforward deal. It's when you start combining the functions into more complex functions that things get a lot more interesting. All right, so we'll build up to that, so just kind of keep that in mind. This first section usually goes pretty well. This is a pretty straightforward process when you're dealing with polynomial functions, especially, or power functions. And actually, I think I'm going to change that. Instead of saying polynomial functions, let's say power functions. It's probably a better word. Let's change that, because not all power functions are polynomials. All right? So this first section, now we'll talk about exponential functions, at least to a certain degree. I'll leave that discussion here for a little bit later. So first, starting off with the derivative of a constant function. Now again, remembering this notation, and this is one of the notations that I brought up in that previous section, that ddx of c. In this case, it's the derivative of our function. It's the change of the function with respect to the change in x. Remember I tell you that little notation, that little d kind of represents change. So this would mean the change with respect to the change in x of that function. But again, if you remember again that the derivative is calculating the slope of the tangent or the slope of the curve, well, remember a constant function If I had a function y equals a constant or f of x equals a constant, remember that's a horizontal line. And we've already mentioned a few times the slope of a horizontal line is 0. So when you're calculating the derivative of a constant function, then you're looking at the slope of that line. Since it's a horizontal line, then its slope is 0. So bottom line, the derivative of a constant is 0, okay? Because the slope of a horizontal line is 0. Next step up, call these power functions, like I said earlier, instead of just polynomials. Power functions. Well, the most basic power function would just be the function f of x equals x or y equals x. And again, if you look at that as just a standalone function, it's a linear function with a slope of 1. And since that's what the derivative measures, the slope of the curve, then the derivative should be equal to 1. So I've got the d dx, or the derivative with respect to x of x, is equal to 1. Or in other words, again, just simply the derivative of x equals 1 because the slope of that line would be 1. And it's a constant slope for linear functions. Right? Then we take a next step up to the more general power rule, which also applies to these other two, but for any function of the form x to the n, right? If we let n be any real number, then the derivative of x to the n is equal to n times x raised to the n minus 1. So in other words, what we're doing, we're finding the derivative of this power function x to the n. We multiply by the exponent, and then we decrease the exponent by 1. And if you recall back to one of the examples that we did in that previous section where we did multiple derivatives for, we started off with f of x equals x cubed minus x, and then we went through the whole limit definition thing to find our derivative, and we end up with the derivative being 3x squared minus 1. So notice that first term, x cubed, if I apply the power rule, I'm multiplying by the exponent and then decreasing the exponent by 1. I get 3x squared. And the second term, which is x, we just said above, the derivative of x is 1. So I get 3x squared minus 1. And each of these functions, each of these derivatives follows the same process, okay, in terms of the power rule. Now again, I'm going to talk about more of that as we go through this section, so we'll kind of leave it at that. But that was one of the functions that we had looked at previously. So let's say, for example, let's differentiate each of the following 3 functions. Now, again, power rule is about as straightforward as you're ever going to get. If I'm looking at the derivative of the function f of x equals x to the 7th. Now, like I said again, initially, first thing you're recognizing is what type of function am I working with? That's always should be your first question. What type of function do I see? It is a power function, so I apply the power rule, which says multiply by the exponent and decrease the exponent by 1. So the derivative of x to the 7th, f prime of x is 7x to the 6th. Now the second function, and this is kind of like when we were dealing with the limits. Remember, we were trying to use direct substitution, and in a lot of cases we couldn't use direct substitution because the a value wasn't in the domain of the function. But maybe we could take the function and rewrite it into an equivalent form that we could use direct substitution. Well, the same thing happens with finding derivatives. I mean, once you develop these rules, these processes with these different types of functions, not only do you have to recognize the type of function when you're looking at it, but also maybe a case like this, where initially this is not written in the form of a power function. It's not x to a power. It's 1 over x squared. However, I can equivalently write that function as x raised to the negative 2 power. And by rewriting it into that equivalent form, I can then apply the power rule. You know, so it becomes another process or situation that you always have to be aware of when you're working with these functions. Not every one initially is going to fit nicely into a mold of I can use this rule or that rule or this process or that process. I may have to recognize that I'm going to have to do a little bit of rewriting to get it into the form or a form that I can then apply one of these processes. And so that's the more difficult part of this, because of course if it's just written basically as a power function, then I can apply power rule and there's no issue. So that's a couple of things we want to make, kind of recognize here in terms of how can I rewrite or recognize power functions just written in different forms. So rewriting that function as x raised to the negative 2 power, I can then apply the power rule. Now be careful with negatives. So I'm multiplying by the exponent, so I've got negative 2, and then you have to decrease that exponent by 1. Be careful with your negatives, right? Because if I take negative 2 and subtract 1, I get negative 3. Sometimes we make mistakes there, and I know it's not intentional, but that is obviously, just be careful with the negatives. So decreasing negative 2 gives me negative 3. Now, something else we'll have to talk about. Once I find the derivative, because this is the derivative, that's it, I'm done. You then have to make maybe an observation or a choice in terms of, well, how do I want to rewrite this thing? Do I want to leave it as it is, or maybe we can write it into a nicer form? Okay, and really that is going to just depend upon maybe how complex the function is. Sometimes we're just, I'm mainly interested in finding the derivative, obviously. That's our first and foremost objective. But once you find the derivative, we may need to rewrite the function. We may choose to rewrite the function into a different form. So there's nothing wrong with negative 2x to the negative 3 power. And that's perfectly good equation for f prime of x. We could choose, though, to rewrite that as negative 2 over x cubed, to rewrite it without the negative exponent. And just when you're working homework problems, keep that in mind. You may choose to write it one way, and then when you check your solution, it's written a different way. That's fine, as long as you can see how to take what you have and put it into the form of what they have, or vice versa. In other words, as long as what you have is equivalent, that's fine. So, all I always say with these, let's just at least try to clean them up and make them look as presentable as possible without making that the main objective, right? So, I don't want to get caught up and bogged down with having to rewrite this function into, doing a bunch of rewriting and simplification with the function itself, where that ends up being the bigger issue as opposed to actually finding the derivative, right? So not a real big deal at this point, because we're still kind of dealing with basic functions. But as we start looking at functions that are more complex and have more moving parts to them, it's going to become a bigger issue. It's like, okay, once I find the derivative, great, that's one thing. What do I then do to rewrite the function into as simple a form as possible? All right, so we'll have more discussion as we go with that. So negative 2x to the negative 3 is the derivative of that function, perfectly fine. We could also choose to rewrite it as negative 2 over x cubed. That's an equivalent form. It just looks nicer because we've gotten rid of the negative exponent. Number 3, here's another prime example of having to first rewrite the function. So f of x equals the cube root of x. That's our function. So again, it's not written in a form that I can work with initially, but remember, I can write radical notation in exponential form. So the cube root of x can be rewritten equivalently as x to the 1/3 power. And now I've got a power function, right? It's written in the form of a power function. I can use our power rule. Now, yes, you're going to have to work with fractions here. We are big boys and girls. I trust you can do basic fraction calculations, but yeah, I know sometimes that's an issue. So what is my process for the power function? I multiply by the exponent, 1/3, and then I have to decrease that exponent by 1. Well, if I take 1/3 and subtract 1, 1/3 minus 3/3, I get negative 2/3. So the derivative of f prime of x, is 1/3 x to the negative 2/3. And then again, just like the previous, it's a question of, well, what do you want to do to rewrite it? So again, there's nothing wrong with what I have there first, 1/3 x to the negative 2/3. Again, we could choose to rewrite it so that the exponent is not negative, so I've got 1 over 3x to the positive 2/3. Perfectly fine. We could also then choose to rewrite it back into radical form, which would be the cube root of x squared. All right. Now, do I have to do that? No, not necessarily. And a lot of times it really will depend upon if there's anything else we want to do with that function moving forward. So that's my final answer. Yeah, this is perfectly fine. What I have here, maybe we choose to at least do this to get rid of the negative exponent. Whether or not you choose to write it in radical form, that's usually not as big of an issue. Leaving it in exponential form is usually fine. Now you see, notice I'm not giving you any 100% on any of this because it just kind of depends on what we choose to do at the moment. And like I said, you're going to look in the solutions manual when you're doing these, and you'll see in some cases they choose to leave the negative exponent. In other cases, they rewrite it without the negative exponent. And in other cases, they'll put the radical, So it just depends on who was doing that particular problem in the solutions manual in terms of how they ultimately choose to write it. But again, I'm not that concerned with that at this point. We'll talk more about that going forward. Next process or next rule, the constant multiple rule. This is similar to what we saw with limits. If c is a constant and f is a differentiable function, then the derivative of the constant times our function is equal to that constant times the derivative of the function. All right. Or in other words, the derivative of c times f of x is equal to c times f prime of x. All right. So again, very much similar to the limit laws, right, where the limit of a constant multiple of a function is the constant times the limit. Same thing is true here for the derivatives. Now, a couple of examples, and I'm going to break these down into their minutest steps, all right, just to illustrate these rules. But definitely, you can consolidate steps here. So the first one, f of x equals 5x squared. I'm just emphasizing the fact that this is the constant 5 times the function x squared. So if I'm differentiating a constant times a function, f prime of x would then be equal to that constant times the derivative of the function. And now I'm differentiating the basic power function x squared, whose derivative is 2x, so I've got the constant times 2x, which then gives us 10x. Okay? Now, do you have to write that out in those steps every time? Absolutely not. If you can go straight from here to here, that's fine. All right, so notice in the case of a power function, when you multiply by that exponent, you're going to multiply the coefficient by that exponent. So it's 5 times 2 is 10, and then we decrease the exponent by 1 to leave us with x. Okay, but again, this is just illustrating what's happening with the constant multiple rule. You can definitely consolidate steps there. You do not have to break it down that minutely. Okay, that's fine. The second one is another example with a radical. All right, so again, first I rewrote the function. Instead of square root of x, I rewrote that. I rewrote that as x to the 1/2. So that again, we can apply our power rule. All right, so again, I did the little constant multiple thing. And also notice too, again, and I've mentioned this to you before, make sure you clearly label what the function is that you're working with. In other words, here's f of x, my original function. And then once I start the differentiation process, I want to label that as f prime of x, or y prime, or whatever notation we're using at the time. So you want to clearly indicate which function is which. Right? What is my function? What is the derivative? Everything should be labeled clearly. Okay? We don't want any misunderstandings with that. So yeah, you call it what it is. All right, so then our derivative, again, it's the constant times the derivative of the function. All right. So then our derivative of x to the 1/2. And this is maybe a good one to know. I'll talk about this one in a minute because that's the square root of x. That's a pretty basic common function. So the derivative of x to the 1/2, we're using our power rule, would be 1/2 times x. If we decrease the exponent by 1, 1/2 minus 1 gives me negative 1/2. So I've got that constant times the derivative of our function. And then here I've got 2 times 1/2, which is 1. I mean, that'll give me 1. And so we're left with just x to the negative 1/2 as our derivative, which again from here, how do we choose to rewrite it? So rewriting it with the positive exponent, 1 over x to the positive 1/2, and then I put it back in radical form. And again, that's just a matter of choice or what the situation dictates. The sum rule and difference rule. Pretty basic rule. This is very similar to what we saw with limits. If f and g are both differentiable functions, then the derivative of a sum of two functions is equal to the sum of their derivatives. the derivative of the difference of two functions is equal to the derivative difference of their derivatives. Right? And that was, again, that was true for the limits. The limit of a sum, limit of a difference was equal to the sum of the limits or the difference of the limits. But notice there's something different here. There's no product and quotient. All right? And you have to distinguish between the two things that we're working with when you're talking limits. Right? Remember, a limit is a function value as x approaches a. Right? The limit as x approaches a of f of x equals L. And so there's a product and quotient rule similar to this sum and difference rule that held true for limits. Right? The limit of a product was product of limits, and limit of a quotient was quotient of limits. That's not true for derivatives. Now remember, the derivative is a special type of limit. Remember, with the derivative, we're finding the slope of the curve. Right? We're not talking about what the function value is approaching as x approaches a. Okay. So yes, it is still a limit, but it's a special limit in that we're calculating that limit of the slopes of the secant lines to give us the slope of the tan line. So the product and quotient rule that is true for limits is not true for derivatives. Okay, and I'll show you why once we get to that point. So okay, what if I do have a product? I'll show you why that's not true. But here's the big deal with this one. It's a pretty straightforward rule. But what it allows us to do, ultimately then, is take a function that has multiple terms, and you can differentiate it term by term. All right, now I'm not going to have you, like we did with the limit laws, you're not going to have to break this thing up into minute steps and all that. I think we're past that point. We can consolidate steps. But basically, that's what this allows us to do. Now, just like with the previous ones, that just depends on if the function is written in a form that I can do that with. All right, so number one, pretty straightforward. F of x is this little polynomial, 5x to the 8th minus 2x to the 5th plus 6th. So basically, the power function, I just differentiated term by term, and I went ahead and consolidated steps on these, so that if I find the derivative of 5x to the 8th, using our power rule, 8 times 5 is 40, and then we decrease the exponent by 1. So f prime of x would equal 40x to the 7th. Same thing with 2x to the 5th, right? We multiply 5 times 2 to get 10, and that should be 10x to the 4th, decrease the exponent by 1, and then plus the derivative of 6. Now remember, the derivative of a constant, that was when we started off with, derivative of a constant is 0. All right? So obviously I don't need to write that, so I didn't. But that's just basic power rule, and it's term by term. Number 2, here's a case where, again, I'm first rewriting the function. Notice I've got x squared minus 2 square roots of x over x. That's a quotient. All right, that we just got through saying there is no quotient rule that says we'll just take the derivative of the numerator divided by the derivative of the denominator. All right, there is no quotient rule that allows me to do that. Now, there is a quotient rule, but that's not it. It's a lot more complicated than that. We'll talk about that in an upcoming section. But what I want you to recognize here is you do have an option. You do have a way of rewriting this function so that you can actually then use power rule, okay, which ends up being a heck of a lot simpler than the quotient rule that we're going to talk about later. So given that option, right, and we'll mention that too as we come across different processes. Sometimes you do have choices. It's not that there's only one process or one method that works for each type of function that you run into. You may have choices in terms of how you choose to rewrite the function and which method you choose to use to differentiate the function, depending upon how you choose to rewrite it. And obviously, some methods are going to be a little bit quicker or more efficient than others. So it may be a matter of trying to find the most efficient way. But bottom line, you have to get it done, right? So, I mean, if you're presented with multiple options, you can do it either way. But you may save yourself a lot of work if you recognize which way is more efficient. And so again, we'll talk more about that as we get into more processes. So what I want you to remember in this case is if I have a fraction, a rational function, that has a single term denominator, I can rewrite that function by separating the terms of the numerator and placing each of those over the denominator. Right? So I can rewrite this as x squared over x minus 2 square roots of x over x. And then what I did next was I just Well, before I simplified, I went ahead and rewrote the square root of x as x to the 1/2 to remind us, right? Because once you rewrite that, now I can simplify using rules of exponents, okay? So don't forget that. If I have that square root or radical of any type, I can always put that in exponential form. And that's the advantage of the exponential form. You can then use rules of exponents. Now, what's the rule of exponents with fractions? If I've got x squared over x, I subtract the exponents, 2 minus 1. So that leaves me with x. Or with that one, you could simply say if I have x squared over x, I could divide out a common factor of x. But the broader rule that's in play here is you're subtracting the exponents, 2 minus 1, to give me x to the first. Because that works a little bit better with the second one where I have 1/2 minus 1, which gives us negative 1/2. And so I'm rewriting that second term as minus 2x to the negative 1/2. So that's straight rules of exponents. So that works better instead of thinking of it in terms of just simplifying. Follow the rules of exponents. Subtract the exponent of the numerator minus the exponent of the denominator, and what you get becomes your new exponent. And now we have this function ready to use power rule. So there's our derivative of x, which is 1. Now I then, in the second term, remember we multiply by the exponent. So if I take negative 1/2 and multiply by 2, it's negative 2. That gives me a positive 1 as our new coefficient. And then we have to decrease the exponent by 1. If I take negative 1/2 and subtract 1, negative 1/2 minus 2/2 gives me negative 3/2. So this is our derivative. Perfectly good derivative. And then again, like we say, how do you want to rewrite it from there? All right, and like I said, a lot of this will just depend on how complex the function is. At some point, I said the function gets, complex, has a lot of different pieces to it. We may just leave the negative exponent and not bother with it, because again, it's all about the derivative. I don't want to spend a bunch of time having to rewrite the function. We at least clean it up as much as we can. But again, here are some different options here, right? So I can rewrite that again without the negative exponent, so 1 over x to the 3/2, which I can then convert back to radical form if you wish, would be the square root of x cubed, which then if you chose to simplify that, would be x times the square root of x. Now I'm not going to get into all that. If you remember how to simplify the radicals, great. If not, square root of x cubed is perfectly fine. Okay. But again, any one of those, this one that I have circled, or this one, or this one, or this one, any one of those is acceptable for the derivative of that function. But notice again, we're using different notations, right? So instead of f of x and f prime of x, here I started with y equals, so I'm calling it y prime. Right? So you want your derivative to match the notation. Okay. All right, so that's our power rule for dealing with power functions, or a function that I can put in the form of a power function. Exponential functions, I want to talk about those a little bit in this section. Now, we're not going to do a complete discussion of exponential functions because we do need more tools in order to address every possible exponential function. But we can at least deal with one exponential function in this section. That's what we're going to work with. And then we'll have to come back and talk more about exponential functions later as we come up with more tools. But here's what I want to look at in this case. So we'll start off with an exponential function of the form f of x equals a to the x. Remember, that's our basic exponential function of base a. Find our derivative, f prime of x. We can use the limit definition, and like we keep talking about all these tools we're throwing in the toolbox. If I don't have a process directly that I can use to find the derivative, then we can fall back upon the limit definition. That was the whole point of looking at that. That does give us a method for differentiating any given function. So here's our limit definition. Remember that limit as h approaches 0 of f of x plus h minus f of x over h. That was our limit definition of the derivative, where in this case f of x is a to the x. So f of x plus h would be a to the x plus h minus f of x over h. The next step, I applied one of our rules of exponents. Remember that when you multiply bases or like bases, so in this case, if I look at a to the x times a to the h, what do you do with the exponents when you multiply like bases? You add them. So all I did here was take that rule in reverse. We're not used to doing that, but remember, these rules work. So if you had something like this, these rules work in both directions, right? So normally we don't think about doing that because we do the calculation in our head. So x squared times x cubed is x to the 2 plus 3, which gives us x to the 5th. So it works in reverse as well. So if I have the exponent that is a sum, then I can break that exponent up and I can multiply by like bases. So a to the x plus h would be equivalent to a to the x times a to the h. Keep that in mind, because like I said, these are all different techniques and tools that we use to rewrite these expressions and functions. So you have to be familiar with all those basic rules of exponents and so forth. All right, so the rest of it remained the same. I still have minus a to the x over h. And then I took that numerator, since both terms up there have an a to the x factor, so I can factor out a to the x out of that numerator. It leaves me with a to the h minus 1 all over h. And then I just rewrote it by pulling the a to the x out of the fraction, and equivalently that would be a to the x times a to the h minus 1 over h. I mean, that is equivalent to the previous statement. You just multiply them by a to the x. Then the next step here, I want to mention this with respect to limits, right? This is a limit with respect to the change in h, right? The limit as h approaches 0. There's no h in this factor, right? That's a to the x times this expression which contains the h. A to the x does not have an h in it. So in other words, as h changes, as h approaches 0, what happens to the value of a to the x? It doesn't change. All right? The change in h is going to change this part. It's not going to affect this part. And since the value of a to the x doesn't change, then what does that make it? That makes it a constant. So whatever a to the x is, depending upon the base a, for per specific function, that value does not change as h approaches 0. So we can treat that as a constant. So that brings me back to that constant multiple rule that we just looked at, or that we, not just for derivatives, but the limits, that said the limit of a constant times a function is the constant times the limit of the function. So this is our constant multiple rule for a limit. So I can go ahead and pull that factor of a to the x out of our limit. It's a constant factor. And then we're left with this limit as h approaches 0 of a to the h minus 1 over h. Now, hanging on to that for a second, let's go down below and let's consider f prime at 0. All right, so for the function f prime of x, or f of x equals a to the x, what is f prime at 0? All right, so this is going back and using all those tools that we used in the earlier chapter. So here's our limit definition again. Its limit as h approaches 0 of f of 0 plus h, because right, now a is 0, f prime of 0. So it's a to the 0 plus h minus a to the 0, because I'm plugging in 0 in place of x, all over h, which leaves me with the limit as h approaches 0 of a to the h. And remember, a to the 0, there's another rule of exponents, any constant, non-zero constant, raised to the 0 power has a value of 1. So a to the 0 plus h is just a to the h. A to the 0 is 1 over h. But notice that's exactly what we had above, right? So I mean, this limit statement is the same as the one right above it. But what is this one? This came from what? F prime at 0, or f prime of 0. So in other words, all of this, when all of this is said and done, and of course all I'm really interested in is the ultimate result of this thing, but I want to show you where all this stuff comes from so you understand why it is what it is. So remember, all of this started with finding the derivative of f prime of x. So what is f prime of x? f prime of x then is equal to a to the x times this, which is f prime of 0. Okay. So for f of x, I'm just going to note that again down here. Our basic exponential function, f prime of x is, notice it's the function itself, it's still a to the x, times the derivative of the function at 0. Now, that's a little problematic. I mean, that's like using the word in the definition, right? I can't define a word by using the word itself in its own definition. So if I'm saying f prime of x is a to the x times f prime of 0, how do I find the derivative of a function if I don't know the derivative of the function? Okay. So we're going to address that here in just a second. But at least that gets me to that point. But what we do also want to recognize is that for exponential functions, the rate of change of that function, right, the derivative, is proportional to the function itself. Right? Because f prime of 0, that's just going to be some number. That's going to be a constant value. It's whatever the slope of the curve is at 0. Right? So the derivative of a to the x is that function times some constant value. Now, there is one exponential function that we can deal with at this point. And that's our good old friend, the natural exponential function that we talked about back in the review section. For f of x equals e to the x, right, our natural exponential function, the slope of the tan line at the point where x equals 0 is 1. That was one of the definitions I gave you at that time for that base e. Right? We looked at f of x equals e to the x, and that was one of the observations that we made was it was the exponential function where the slope of the tangent line at the point where x equals 0 was 1. Well, again, what is that? The slope of the tangent line at x equals 0, that's f prime is 0, right? Because that's what our derivative is. It's the slope of the tan line. Below that, I just threw in the limit definition again. So if we look at f prime of 0 with respect to e to the x, then it's the limit as h approaches 0 of e to the 0 plus h minus e to the 0 over h. But ultimately, all I care about is the fact that that equals 1. So now we can go back to our f of x equals a to the x that we just talked about, specifically when a equals e. So for f of x equals e to the x, the derivative, f prime of x, according to our previous work, was the function itself times its derivative at 0, which for e to the x happens to be 1, which, how convenient is that? So the derivative of e to the x is e to the x. So here's a case where I have a function that is its own derivative. Now, that's definitely as straightforward as you can get. So that makes e to the x one of our friendly functions. And that was part of my reason for doing that review on exponential and log functions, because you work with these a lot, and you're going to see a lot of e to the x functions. And I told you at the time, we don't call it the natural exponential function for nothing. It's the exponential function base e because that number e just pops up in a lot of naturally occurring situations. And it's all over the place in the real world. So it's a very common function, very popular function. Nicely, conveniently, the derivative of e to the x is e to the x. So then if we want to differentiate the function, say 3e to the x, or y equals 3e to the x plus 5x, right? I mean, the constant multiple rule still applies here. Obviously, I mean, and that's what I was talking about earlier, different types of functions versus processes, right? So I'm differentiating here 3e to the x, which is our exponential function base e. I'm differentiating here a power function, 5x, right? And with respect to each one, you could also apply the constant multiple rule. So I went ahead and did that again here just for illustration. So y prime, again, this is our function, y equals, so then our derivative I'm calling y prime. And y prime then would equal to that constant times the derivative of the function. Now the derivative of 5x, remember, would be just 5, right? The derivative of x is 1 times that constant. So then I end up with y prime equal to 3e to the x plus 5. Now again, as I said before, you don't have to include this middle step. If you can go straight from here to here, that's perfectly fine. And I expect that you should be able to do that. I mean, you know, for these constant multiple rules, I don't expect that you would need to write that middle step out. But yeah, if you find it helpful, write it out. That's fine. So in other words, the derivative of a constant times e to the x is still just constant times e to the x. So the derivative of 3e to the x is 3e to the x. And then, as we already said, the derivative of 5x would be 5. So there's our derivative, right? So y equals 3e to the x plus 5x. Y prime is 3e to the x plus 5. Last question in this section, last example. This is going to get into something, again, we've talked about before. I tell you, we're going to start applying more and more what the derivative actually tells me about the behavior of a function or the shape of the graph of a function. Question is, for what values of x does the graph of f of x equal x cubed plus x squared minus x plus 5 have a horizontal tangent? So that goes back to, we've talked about horizontal tangents before. Where do you find horizontal tangents, or what does that tell me about the graph? We find a horizontal tangent wherever the slope of the curve would be 0, right? Because the slope of the horizontal line is 0. So with this question, the interpretation is, if I want to know where the function has a horizontal tangent, how do I find that? Well, I said its derivative equal to 0, because that's where you find horizontal tangents. That's horizontal lines, slope of 0. So there's the implication, right? So of course it's the interpretation on your part. After that, we'll do exactly what we just said. Let's set the derivative equal to 0. So I take my function f of x equals x cubed plus x squared minus x plus 5. Go ahead and find our derivative. Now that's a nice little polynomial power function. So the derivative of x cubed would be 3x squared, I multiply by the exponent, decreased by 1. Plus the derivative of x squared, which again, multiply by the exponent, decreased by 1, 2x. Minus the derivative of x, which is 1. And then we have the derivative of the constant, 5, which again, the derivative of the constant is 0. But we don't need to write that. So there's our derivative, and then we're setting the derivative equal to 0 to find the point at which we have a horizontal tangent. Where is the slope 0? So that's what the question that you're asking here. Where is the derivative equal to 0? And now it becomes a matter of solving the equation, and that's just going to depend on whatever type of equation you end up with, depending upon the type of function that you have. We're going to see this type of question pop up on occasion. And again, it's one of those things that's going to play a big part in the applications when we get to that part. We're always interested in where you have those horizontal tangents, where the derivative is 0, or the rate of change is 0, where you have those turning points and that kind of thing on the graph. So here we're just solving the equation. I mean, that's a quadratic polynomial, so this one factors. So I went ahead and factored it, 3x minus 1x plus 1 equals 0. Set each factor equal to 0. And I've got x equals 1/3 and x equals -1. And of course, I trust that you can solve a basic polynomial equation. So x equals 1/3, x equals -1. Those should be the points on the graph where you see horizontal tangents. And if you go back to the graph that I have sketched below, that's the graph of the function. You do have that horizontal tangent at the point where x equals -1, and you have a horizontal tangent at the point where x equals 1/3. Okay. We're going to do a lot more of that going forward, because that is definitely useful in terms of describing the behavior of a graph. And then, like I said, there's going to be a lot of applications with that kind of thing. Now, we're going to have to deal with the exponential functions in more detail later. Right? I mean, this is only one exponential function, right? It's the natural exponential function base e. What if the base is something other than e? Okay, so but we need more tools in order to address that, so we will address that later in this chapter. Okay? And that is it for section 3.1.